All right, this is the the last section. First, again, the Newton's method. The Newton's method. Last section is iterative. That one is very lengthy because you have to start off with an initial condition, and then you have to keep on repeating the process over and over and over until you come to an optimal solution. By hand, it's time-consuming. With a computer, you have to first write the algorithm and then run it through so many iterations. So I'm thinking about taking that one off our list. So this will be the last one for this chapter. Chapter 4, Section 6, Optimization. What's optimization? When you hear the phrase, the word optimization, what does that mean? Or optimize, what does that mean? What's that? Yeah, you have a condition that you want to meet. Like, for example, give me an example of most efficient for an optimization problem. Okay, it's all everywhere around you. The bottles of stuff you drink, the cans of drinks you have, each one of those have been designed mathematically first. Because the companies know how much it costs to produce the product, and they want to minimize the expense of putting it in a container, which in essence maximizes their return on profit on investment. All this stuff is done mathematically, optimization problems. So, for example, the can of Red Bull, what dimension should it be if we want to maximize the profit? Because if you make it too small, nobody's going to buy it. If you make it too big, you're losing money. So there has to be a point where you can maximize your profit. And that's what we're going to look at today. All right, so most efficient, effective, best to either maximize or minimize the desired result. You want to maximize profit, you want to minimize waste. Or you want to maximize production, you want to minimize exposure. So that's what all these are looking at. Here's the worst part. They are all word problems. That's the worst part. Because I know you have a hard time and you cringe whenever I write, I'm typing them out. Example 1. An open top box is to be made. Let me see. Okay, can everybody still see? Oh, I should have said luminous. Open top box top is to be made by cutting small congruent squares from the corners of a 12 by 12 inch sheet of tin and bending up the sides. How large should the squares be cut from the corners to make the box hold as much as possible? Where do you start with this kind of problem? Draw a picture. Yes. So we have a 12 by 12 sheet of tin. Inches by 12 inches. Okay, what else does it tell us? We know the sheet is 12 by 12. What else is important in that sentence, in that paragraph? By cutting small congruent squares from the corners. So each corner will have the same size bit clipped off. Do we know the size of it, of those corners? So what do we label those? If they're not known, what do we label it? X. That's the unknown. Because it does two things. It tells us how big of a corner we cut out. And what's the second thing it tells us? What's X going to tell us once we find it? The depth of the box. Because we have to fold up the sides, so that X amount will be the height of the box. Okay, so we draw a picture, label what we know. Now we got to put it into an equation. What equation do you think we'll use here? We're talking about a box. So what kind of formula do you use for a box? What kind of equation do you use for a box of holding things? Inside a box. What? Area. What's the formula for area? Base times height. Wouldn't hold too much because when you pick it up, they fall off the sides. What's the next part? If you take the area, that's this side, and you fold up the sides, you now have what? Volume. Base, height, length. It's got to be three dimensions. You have to have a base, a width, and a height. I'll use width instead. Width. Now, how do we find these variables? Do we know the height? Which variable is going to go with the height? That's the x. So that's the height. How are we going to figure out the dimensions of the area part, the flat part, the bottom? What do we know about this side? Okay, it's 12 inches. Is it always 12 inches? Minus what? 2 x's. Because we're going to clip, whatever size those x's are, we're going to clip those. That means this length here will be 12 inches minus however big those are. Do we have one of those or two of them? Because remember, it's a square. So the length and the width are the same dimensions. So the volume can be written as this. Do we have a domain that we have to stay within? Well, 12. Remember, domain is the x values. Can we put 12 in here? Yeah, so it could be the domain can be anywhere from 0. How big? Remember, you have to take the same amount from both corners. How big can each corner be? Maximum is 6 inches, yes. Because if this corner is 6 inches and that's corner, that takes care of the entire side. Another way you could have done it is take this inside equation, 12 minus 2x, and solve for x. We know it could be 0 because, well, we don't have to have one. Now what do? We have the formula of our volume. We have the domain. We have the endpoints of our function. What do we do next? Optimization. We're looking for the maximum or minimum. Have we talked about those previously? Maximum minimums? How do we find the maximum minimums previously? Yes. So, we have to take the derivative of our volume with respect to which variable? What? The x. Why the x? Because that's the part of the tin sheet that's variable. Depending on the size of the x, that tells you whether you have a maximum or minimum volume. So take the derivative of this function here. What method are you going to use? We're going to use the product rule first, but we have to use the power rule for this function. So the f is x, the g of x is 12 minus 2x squared. What's f prime? G prime. Take the derivative of the outside, which is 2, leave the inside alone, times what? Derivative of the inside. The derivative of the inside is going to be negative 2. So that's negative 4, 12 minus 2x. Since we're doing a product, we could do the fishy thingy with a plus. Twelve minus 2x squared times 1 plus x times negative 4, 12 minus 2x. It's 2x squared plus x, distribute them inside, negative 48 plus 8x. So how would you solve this part next? All inside here, I just multiplied the negative 4 times, I went ahead and worked this one out. Negative 48 plus 8x. Up here you could have. Okay, you want to do that way? Okay, so we're going to go from here. So we're going to take factor out of 12 minus 2x. That will leave us 12 minus 2x plus x times negative 4. Inside here we got 12 minus 2x minus 4x minus 2x minus 6x. Now what are you going to do? This is our dv dx. Very good. Because the function has to be set equal to 0 to find a optimization, a maximum minimum. So by the zero product principle, since we have two linear terms equal 0, set both of those individually equal 0. We got 12 equals 2x, x equals 6. 12 equals 6x, x equals 2. Is there another one? Because the function itself has an x in front, we could always look at the endpoints. So we have x equals 6. We also look at x equals 0. Remember, always look at the endpoints in case those are the maximum minima, and look at the intermediary point. Intermediary point is 2. What do you do with those now? Very good. Find v of 6, find v of 2, and find v of 0. It's 6 times 12 minus 2 times 6 squared. 2, 12 minus 2 times 2 squared. Anything is 0. Okay, so the endpoints give us 0. Don't think they're going to be maximum. So our maximum is going to come with this middle one. Two times 64, 28. 128, what units were these? Inches. So cubic inches. So our optimal box will look like what? What will the dimensions of our optimal box be? I just want the dimensions. We know the optimal volume is 128 cubic inches when x equals 2. So what are my dimensions of my box? 8 inches by 8 inches by 2 inches. 8 inches wide, 8 inches long, and 2 inches high. Any questions about that? Let's look at cylindrical sphere. Or there. You've been asked to design a 1-liter can shaped like a right cylinder. What is a right cylinder? What do you think a right cylinder would mean? If you look at a cylinder, what does a cylinder look like? Something round. If you look at a cylinder sideways, you see a rectangle. The corners are all 90 degrees. That's what a right cylinder means. It doesn't have any beveled edges. So what dimensions will use the minimum material? Think of this now. How is this one different than the first one we just did? We're looking for the least material. The last one, we looked at the volume. The material to make a cylinder would be the surface area, the outside of it, the surroundings of it, not the inside. So we have to figure out, in that case, what is the area of a cylinder, a right cylinder? Look at the pieces. What are the areas on the top and bottom? You have, on top and bottom, you have circles. What's the area of a circle? That's circumference. R squared. Actually, I'm glad you said that, because the area and volume or circumference, all this stuff relates to each other. But you told me 2 pi r, right? If you take the derivative of pi r squared, what do you get? 2 pi r. So that's the relationship between them. So, and how many of these areas do we have? How many circles do we have in a cylinder? 2. So it's 2 pi r squared. That's for the top and bottom. Now, what is the surface area of a cylinder? The circumference is 2 pi r. The circumference is the outer area. The area is the inner area. Since we're looking for the skin of this thing, we're looking for 2 pi r. What's missing? The height, h. So this one's going to be 2 pi r h. So the area of this object, of this cylinder, is the top and bottom are 2 pi r squares, and then the skin of the outermost of the cylinder is 2 pi r h. What are we looking for? Well, it's got to be what? 1 liter can. Typically, when you look at volumes for fluids, you use centimeters. So 1 liter is the same thing as 1,000, centiliters, not centimeters, centiliters. Okay. Now we got to start putting this stuff together. We drew a picture. We have the formula. We're looking for the maximum or minimum. Minimum. How do we get that? What do we have to do next? We can't really take a derivative of this. Why? How many variables are in there? We have the radius and the height. We have to find one of these variables in terms of the other variable. It's easier to figure this one out, since it's only one of those. What's the formula for the height? So we know that 2 pi r h has to be the volume of it, or what it contains. It's a 1 liter can. So h would equal to the 1 liter over 2 pi r. So h is that. Where do we put that? Put that back in our equation, because now we're going to have to do what? Let me see. Hold it, so it's 2 pi r squared plus 2 pi r h equals 1 liter. Two pi r h. Gotta be squared because we're looking at the area of it. Looking at the area. Simplify this part. Ice cancel. We simplified this whole section here. Now we have one equation, one variable. Because we're looking for an optimization, we're taking a derivative with respect to the radius. That's the only variable that's left. Which equals 2 pi r squared, which makes it 4r. The derivative of this one is going to be negative 100 over r squared. Derivative of this one is going to be 4 pi r, and this one's going to be the derivative of that, which is 100 times r to the power negative 1. Negative 1 r minus 2. Which is that. What do we set this equal to? What's that? Oh, actually, what is our domain? What are the bounds of our function? Yeah, 0 is always one of them, but we can't use it because it's on the bottom. But that's the lowest bound. We can't use negatives because it'll never be negative. Then what? Not the original. First derivative. Yes, we could set this one equal to 0. So we get 4 pi r equals 1,000 r squared. What are we solving for? R. We got 4 pi r cubed equals 1,000 over 4 over 4 pi. So that equals 250 over pi. Cube root both sides. And r equals to the cube root of 250 times pi over pi. What would happen if we took the second derivative of this? What would that tell us? Concavity. Concavity would tell us what about the function? Concavity. If it's concave up, what does that mean? The bowl opens up. If it's concave down, the graph points down. In other words, if the second derivative is always positive, what does that tell you about the function? The ever-increasing function. Which is what would happen if we did that to our function here. Because this would be 4 pi. It could be never negative. This would change that to positive. So it would be 1 times 1,000 divided by r cubed. And since that's positive, it will always be positive. So it's an ever-increasing function. So our radius is that. It's some value. You get a calculator, it'll be some decimal value. What do you do with it? Well, then you plug it into the formula for the h. 500 over pi r. 500 over the square root of 250 over pi times pi, and that'll give you the height. To minimize the dimensions of this cylinder. Let's look at a physics problem. A rectangle is to be inscribed in a semicircle of radius 2. What is the largest area of the rectangle can have? And what are its dimensions? So first off, we have to do is let's translate what this question is telling us. We know what a rectangle is. What does inscribed mean? Inscribed. What does scribe mean? To write. So a rectangle is to be written inside a semicircle. Of radius 2. Rectangle is supposed to be inside there. So what is that point on the rectangle, on the circle? What is that point? Well, it is going to be tangent, yes, but what's the location of that point? Well, let's see. We know this is x units wide. The length of this box has to be x units wide. Do we know how high it is? Or do we know how far it is from the center? Radius 2. So the hypotenuse is the radius. So we have a triangle that looks like this. Area. Why do we need area? Because it's saying what's the largest area the rectangle can have. In order to find the area, we have to know the length and height. So what's the length of this box? 2x. What's the height? What's the height? Or is there a way we could figure it out? Pythagorean theorem. A squared plus b squared equals c squared. This is A, that's B, and that's C. So x squared plus h squared equals 2 squared. H squared equals 4 minus x squared. The height is the square root of 4 minus x squared. The height. So the formula for the area would be what? Length times height. 2x times radical 4 minus x squared. Are we looking for a maximum or a minimum? Yeah, it says largest. So we're looking for a maximum. So what do we have to do with this function? How do we find the maximum of this function? Take the derivative first. Yes, we have to take the derivative of this function with respect to x. Yet, since it's a product rule, 2x 4 minus x squared to the power 1/2. F prime would give us 2. G prime would give us 1/2 4 minus x squared to negative 1/2 times negative 2x. The 2's cancel, leaving us with negative x over square root of 4 minus x squared. It's G prime. Since it's a product, we add. Two times 4 minus x squared plus, actually it's a minus because of that. 2x squared over minus radical 4 minus x squared. Can we do anything algebraically to fix this? Well, you're right. Okay, you said z equals 0. So we have 2 times radical 4 minus x squared minus 2x squared over 4 minus x squared. What do you do? Not the conjugate. Because if you did that, what will happen there? Both sides. We get the difference of we get difference of two squares. No. Because this is a rational function, this is not. We wouldn't end up with the same function. Good thought though. Its easiest rule of thumb is whenever you have fractions and an equal sign, whenever you have fractions and equal sign, get rid of the fractions. First step, find the LCD, which is what in this case? Square root of 4 minus x squared. Multiply the LCD to each term. So we got radical 4 minus x squared times 0. Radical 4 minus x squared times 2 radical 4 minus x squared. Minus radical 4 minus x squared, 2x squared, radical 4 minus x squared. So the whole purpose of doing this is to get rid of the fractions. Reduce. The radical 4 minus x squared at the end disappear. Multiply and solve. So 4 minus x squared times 0 is 0. Radical 4 minus x squared times 4 minus x squared is 4 minus x squared. Get rid of the radical. E minus 2x squared. Now we solve for x. Distribute. 8 minus 2x squared minus 2x squared. 8 minus 4x squared. X squared equals 8. Divide by 4. X squared equals 2. So what does x equal? Plus or minus square root of 2. So plus radical 2 and minus radical 2. But which one can we not use? Yeah, we can't use a negative because you can't have a negative length. So our x value is positive radical 2. What's our domain of x? That's our intermediary point. Looking at the original one, inside the radical, what's the smallest it can be? Inside a radical. The smallest it can be is 0. You cannot have negatives inside radicals. So what we have to do, we have to take this number, set it equals 0. 4 equals x squared, square root both sides, so x equals 2. The smallest x can be is 0. Again, you can't put negatives. So we looked at the domain because that's the radius of our circle, from 0 to 2. So x has to be between 0 and 2. That's our domain. This is our critical point. Critical value. These are my endpoints. Endpoint 1, endpoint 2. Where do we put them to check to see what they are? In the original equation. Plug in all three of those and see which one becomes the largest. What you got? We have x equals radical 2, x equals 0, and x equals 2. When x is 0, we have 2 times 0, 2 times 0 radical 4 minus 0 squared. 0 times anything is 0, so at 0 it's 0. At 2, 2 times 2, 4 minus 2 squared, 4 times 4 minus 4, radical 0 is 0. So then we're hoping now that our intermediary point will be the saving grace. So 2 radical 2, 4 minus 2, 2 radical 2, radical 2, 2 times 2 is 4. So the optimal largest area we can have is 4. What does that tell us? Remember, these are what they're looking for, the dimensions. So the largest area is 4. When does that happen? When x equals radical 2. The length, remember its formula was 2x. So it's 2 radical 2. It's 4 minus x squared. So it's radical 2. And the area is 4. Economics. We talked about this earlier. Remember we had equations that dealt with revenue, cost, and profit? How do you calculate profit? Revenue minus cost. It's how much money you have coming in minus what it costs you to make the object. The difference of that is your profit. Now, anytime when we look at changes in any of those, we look at marginal cost, marginal revenue, and marginal profit. Those are the changes. And those relate to the derivatives. So the derivative of R, of the revenue, it's your marginal revenue. The derivative of cost is your marginal cost. And the derivative of profit is your marginal profit. So the marginal profit comes from the marginal revenue minus the marginal cost. Here's an example of a business problem. Suppose that the revenue function was 9x, and the cost function was x cubed minus 6x squared plus 15x, where x represents millions of MP3 players produced. Is there a production level that maximizes profit? If so, what is it? It maximizes profit, so we're looking for the largest one. So what is the marginal revenue? Nine. Cost is x cubed minus 6x squared plus 15x. What is the marginal cost? 3x squared minus 12x plus 15. Remember, what are we looking for? We're looking for the maximum profit. Where does that occur? We can find out when do we break even? When the revenue is zero, that means we're going broke. We break even, you say, you can break even when the profit is zero. If the profit is zero, and profit is made up of revenue minus cost, so you break even when the revenue equals cost. So in this case, when the marginal revenue equals the marginal cost, then we start making money after that. This tells us what is the minimum number of MP3 players we have to build to start making a profit. So we have 9 equals 3x squared minus 12x plus 15. It's quadratic. Set it equal to 0, so subtract 9 from both sides. Three x squared minus 12x plus 6 . We can factor out a 3. Unfortunately, we can't just factor it straight out. We're going to have to use the quadratic formula. The quadratic formula is x equals negative b plus or minus the radical b squared minus 4ac over 2a. Where in our example, what are a, b, and c? Yep, exactly. 1, negative 4, and 2. The quadratic formula, quadratic equation is ax squared plus bx plus c. Just plug and play. So it's negative of negative 4 plus or minus negative 4 squared is 4 times 1 times 2 over 2 times 1. Negative negative makes it a positive. Negative 4 squared is positive 16 minus 4 times 1 times 2 is 8 over 2. 16 minus 8 is 8. It's radical 8, since 8 is made up of 2 times 2 times 2, it's the same thing as 2 radical 2. Because if it's square root of 8, it takes, once you have a pair, they come out in front. So our x values are x equals plus or minus, or 2 plus or minus radical 2. x1 is 2 plus radical 2. x2 is 2 minus radical 2. And what do you do with those? Not 0. Remember, we looked at that when we set those. We set those two equal to each other. But yeah, okay, yeah, it would be from 0 because it's a cubic. The original function is cubic, and if x is 0, then 0 equals 0. That's when profit breaks even. And then the other, since they're positive, it goes on to infinity. So we're looking at specifically at 0 and these two values to see which one gives you the highest value in the profits. Remember, profit is revenue minus cost. So you have to find the revenue and the cost with both of those values in there. Subtract them, and look which one's the highest. And that'll tell you which one of your production levels that we have. Because you can't really say infinity because there comes a point where it could start losing money. You're making more than you can sell, so your profits decrease. So that's what we have to be very careful about. But since the cost function is a cubic function and the revenue is a linear function, what we would be looking for is what points do they intersect. Can't be in the negative realm because you can't make negative pieces, so you'd have to see where in the positive realm they do. And we figured that out. That only happens at one place. When x is that. So once you, because it's looking for, is there a production level that maximizes profit? Yes, it would happen whenever we make 2 plus radical 2x items. Or remember, x represents millions of MP3 players. So 2 plus radical 2 million MP3 players, which is a lot. It was pretty much the same thing. So that does it for that chapter.